So this all this thinking about how what's going on with my car and why it's hesitating got me wondering. I wonder how much power I'm actually losing when apparently the gasoline isn't burning the way that it should, right? And I think we can use chemistry to figure that out. I thought it would be cool to maybe calculate, because why not, the force that is being applied on the cylinder head as it goes down. So when the combustion happens here, when the gasoline burns, how much force is going to be pushing down on that cylinder, and how much am I losing out on when my cylinder doesn't work properly, when it doesn't burn and it has that hesitation going uphill. So a couple definitions we have to cover first before we can get to that. First is temperature. So in chemistry, temperature is not just whether something is hot or cold. It's a number, and it doesn't have to do with degrees. It has to do with the average kinetic energy of a particle. Average kinetic. Don't worry about the kids in the background. They're playing outside. Average kinetic energy of the particles. All right. So that means that some are moving faster, some are moving slower, but on average, that's the temperature. So if they're on average moving quickly, that's hot. If they're on average moving slowly, that's slow. The units we use, of course, you're familiar with degrees Fahrenheit and degrees Celsius, but both of those don't actually work when we're talking about gases, because we want whatever zero is to be when the molecules are not moving at all. So 0 degrees Fahrenheit, I don't even know what that is. That doesn't mean anything. 0 degrees Celsius is when water freezes, but the particles are still moving at 0 degrees Celsius. What I want 0 to be like absolute zero, where the particles aren't moving at all. And that is in degrees Kelvin. So Kelvin, which we show with a K, is equal to degrees Celsius plus 273. All right? So that means that basically at a temperature of negative 273 degrees Celsius, the particles stop moving, and that's absolute zero. So we're going to have to keep this in mind for later. All right. The second definition we need is what pressure is. And pressure is caused by particles here, gas particles. This is a container filled with gas. Those gas particles hitting and colliding with the outside of the container, with the walls of the container. So pressure is the force exerted by the particles on the walls of the container. Force of particles pushing on the walls of the container. And for pressure, the units we use for pressure, there's a lot of things. There's like millimeters mercury, there's atmospheres, there's PSI. We're going to use PSI, pounds per square inch. PSI, pounds per square inch. And right now, at sea level, we're underneath 5 miles of air, of atmosphere, and all that air pushing down on us means that for every little square inch of space, there are 14.7 pounds pushing down on it. So atmospheric pressure at sea level is equal to 14.7 psi. All right, 14.7. So how do we use that to figure out how much force is being pushed down on the cylinder? So there's going to be a relationship between temperature and pressure. I mean, if I make a graph that looks like this, with pressure on the y-axis and temperature here, as I increase temperatures, I heat up gas particles, they're going to be moving faster and faster, right? And if they move faster, that means that they're probably going to be hitting the sides of the wall more and more. And if they hit the sides of the wall faster and with more frequency, that means that the pressure pushing out on the sides of the wall would increase. So at a very low temperature, we're going to have low pressure. I guess Charlie's singing out there. And at a very high temperature, we would have a high pressure as the particles move faster and begin hitting the sides of the wall more and more. So as temperature increases, pressure always increases. And that relationship is called Gay-Lussac's law. It's one of 3 or 4 gas laws that you'll find later when you go on AP Chem or take chemistry in college. And it's intuitive. If you increase temperature, pressure increases as well. And we can show that in a formula, okay? And the formula for Gay-Lussac's law is that if you know the pressure in the beginning and the temperature in the beginning, we call those P1 and T1, that is going to be equal to the pressure divided by the temperature in the second condition. So if we know 3 of the 4 of those, we could calculate the one that's missing. So if I know, for example, what the initial temperature and pressure is of this cylinder, and then I know what the final temperature is, so that means I know this one, and this one, I could calculate the pressure that that's being pushed down on the cylinder when it combusts. Let's start filling out this formula here, and let's think about what the pressure and temperature is before any of this, before the combustion happens. So in the beginning, inside the cylinder, we're going to have just regular atmospheric pressure here at sea level. So P1 is going to be equal to 14.7 psi. All right, that's the initial pressure. The initial temperature is going to be equal to room temperature, or let's say an average day like 70 degrees Fahrenheit. That's 20 degrees Celsius. All right, and to turn it into Kelvin, we have to add 273, and we always have to work in Kelvin when we're talking about gases. So 20 plus 273 is equal to 293 degrees Kelvin. So that's the temperature that we're going to use for the initial temperature. Now I'm trying to calculate the pressure in the cylinder in the end, so to do that I'm also going to need T2. So the temperature after this thing combusts, after the gasoline ignites, the combustion temperature in gasoline is close to 900 degrees Fahrenheit, which is about 420 degrees Celsius. So 420 degrees Celsius is what the cylinder burns at in a normal gas engine, and we have to add 273 to that. So that means that in any gas engine, the combustion temperature inside the cylinder when it actually burns is 693 degrees Kelvin. Okay, so let's plug that in here and let's see if we can solve for the pressure inside the cylinder when it combusts, when it burns. All right, so pressure 1 is 14.7 psi, and temperature 1 is 293 degrees Kelvin, and that's going to be equal to, on the other side, pressure 2, which we're going to calculate for, divided by temperature 2, which was 693 degrees Kelvin. So I'm trying to solve for this variable right here. There's a lot of ways you could do that. You could cross multiply and divide. What I like to do is take 14.7 and divide by 293. When I do that, I get 0.0501. So that's 14.7 divided by 293 is 0.0501, and that's equal to P2 over 693. If I want to solve for P2 now, I just need to multiply both sides by 693. And so when I do that, 693 times that, multiply this times 693, what I get is that the final pressure, P2, is equal to 34.7 psi. Okay, so that's my answer for what the pressure is in the cylinder right when the gasoline combusts. So that means that we have inside here a pressure of 34.7 psi. And that pressure is pushing this way, it's pushing this way up here, over there, and it's also pushing down. It's pushing in every direction. So what I want to know is how much of that pressure is pushing down right here on this cylinder head. And in every square inch on that cylinder head, there's going to be 34.7 pounds pushing down on that. So if I want to know the total force, I'm going to have to take the area of this circle right here and multiply it by 34.7, and that will tell me the total force pushing down. So let's remember that the area of a circle is equal to pi r squared, right? So area is going to be equal to 3.14 times the radius of this squared. All right, so how do I know the radius of the cylinder inside my car? Well, luckily you don't have to take your car apart and use a ruler to figure that out. I just went to Google, I'll show you how, and I got a bore diameter of 3.4 inches. To find the size of your cylinder, just type in on Google the make and model of your car. So I've got a 2007 Nissan Sentra. And then you're going to want to type in cylinder bore diameter. Cylinder bore diameter, that's the size of the cylinder. Hit enter, and it usually pops up right there. So mine is between 3.3 and 3.5. So for my calculations, I just took the average, 3.4 inches. That means my radius is equal to 1.7 inches. So I'm going to put that in here, 1.7 inches squared. So when I plug that into my calculator, I get that the area here on the cylinder head is equal to 15.4 square inches. All right? Okay, all right, so if I want to know the total force that's being pushed down on this cylinder, I need to take the pressure, which is 34.7 pounds per square inch, and multiply it by the number of square inches, 15.4. So 15.4 times 34.7 psi is equal to a total downward force of 535.3 pounds. All right. So that's how much is coming down onto that 535.3 pounds. Okay. So that would work. We could be done there, and it would be 535 pounds total, except that we also have atmosphere pushing back up. Remember that pressure pushes in all directions. So pushing back up is a pressure of 14.7 psi. Okay? So we have to subtract that from 535. So on the way up, we're going to have 14.7 pounds per square inch times the area of the cylinder head again, which is 15.4 square inches. All right, and that gives us a total upward force of 226.4 pounds. Okay, so that means 226.4 pounds pushing back up. So then the final answer to this, how much power am I getting from each explosion in that cylinder, is going to be this bigger number pushing down minus that smaller number pushing back up. So that's called the net force. So net force is equal to 535.3 pounds minus 226.4 pounds. And when we do that math, we get 308.9 pounds that are pushing down every time our cylinder goes through combustion. So to me, that is amazing. 308.9 pounds are pushing down every time the cylinder fires. I mean, the cylinder goes up and down, I think we said 150 times a second. Only 1 out of 4 of those is actually a power stroke. So let's say that we've got something like 40 at least combustions happening inside the cylinder every second. So 40 times this, that's a lot of force that we get to put down into the crankshaft to make the car go. Which means that when my car is hesitating and this combustion isn't happening, this is what I'm losing. Every time I feel the car hesitate, I'm losing that much power, which is a big deal. So hopefully, as we move forward, we can figure out how to get these 308 pounds back. Now, that was a lot. The next assignment that I've got in the Google Classroom for you asks you to do this on your own to figure out the diameter of your cylinder in your car. I think it spells out how to do it, but if you there's instructions on there, but if you're confused, go back and watch this again. And let's find out how powerful your car is, because Even though mine's a small car, that's how much it produces. That seems like a lot. All right. Good luck, guys. Caitlin, you ready to go have lunch?
Yeah.
Let's go.